All right, so we are going to be going over the second part um, at the beginning of the semester here. We're going to be talking about Cpctc. We'll get into what that means in a bit. But in order to do that, we need to remember a little bit about biconditional statements from earlier in the year. So let me use the definition of congruent triangles to talk about that. Definitions in general are good things for us to write as biconditional statements. So here is the definition of congruent triangles. Two triangles are congruent if and only if all corresponding parts are congruent. So that means that all of the sides and all of the angles that correspond are congruent. So the reason that we write definitions as biconditional statements is so that when we give something a name, a geometric figure, for instance, a name like congruent triangles, then that means that it has some really specific properties associated with it. But also we know that if something were to have those properties, then we can call it by that name. Biconditional statements really combine two separate conditional statements into one. And that if and only if part is how we know it's a biconditional statement. So here are the two conditional statements that actually make it up. So it says, if two triangles are congruent, then all the corresponding parts are congruent. Makes sense. If all corresponding parts are congruent, then the two triangles are congruent. Also makes sense, right? In fact, this is the way that we've been proving that two triangles are congruent to each other, right? If we knew that all of the parts of these two triangles here were congruent, then we would say, well, that means that they have to be congruent to each other. This one right here, while also something that we've used here and there as we've been discussing congruent triangles, is actually going to be the key to Cpctc. If we have two triangles and we know that they're congruent, then that means that any and all corresponding parts are going to be congruent. Again, that's going to be the key to Cpctc. All right. So Cpctc, that stands for this. The corresponding parts of congruent triangles are congruent. Again, just parsing that out, hopefully it makes sense in terms of what this means, that the corresponding parts of congruent triangles are going to be congruent. So if the triangles are congruent, then the corresponding parts are congruent, right? That's what this conditional statement is here, right? That's what that conditional statement is right here, which was part of the definition of congruent triangles. Again, we're going to be calling this Cpctc, but really what we're really relying on here is the definition of congruent triangles in order to make these statements. But again, we are going to refer to it as Cpctc when we write proofs or do other things with it. And we just abbreviate it that way because it's a mouthful to say the other part every time. Okay. Right. So here we go. Here's how we can use it. So using the image above, how can we prove that angle P is congruent to angle T? Well, those two angles are obvious here to see that we're talking about these two angles. And we don't know anything about the angles of these triangles. So how could we show this? If we don't know anything about the angles, why would those two angles be congruent? Well, it turns out we do have enough information to say that these two triangles are congruent by SSS, right? We have one pair of congruent sides, another pair of congruent sides, and another pair of congruent sides. So we could say that triangle PQW is congruent to triangle TSW by SSS, by side-side-side triangle congruence. And then, if we use that conditional statement before, that remember says if two triangles are congruent, then all of the corresponding parts are congruent. Well, these angles are just corresponding parts. Since I know that the triangles are congruent, I can say that angle P is congruent to angle T by Cpctc. That's how we use it. It's that simple. Nothing more complicated than that. Essentially, we're kind of adding one more step onto what would already be a triangle congruence proof. Let's look at it a little bit more, not necessarily do everything for a full 2-column proof, but let's go ahead and see a little bit more of what this looks like. All right, given triangle TUV and triangle WXV, and we have some congruences here. TV, sorry, I keep doing that. TV is congruent to WV, so TV, WV. And TW bisects UX, so UX is being cut in half, so these parts are equal. This segment right here, TW, cuts the other one in half. All right, well, that's actually a lot of information. We are trying to show that these two sides are equal. So we're trying to show that TU is congruent to WX. Well, I don't know anything that can directly show that. There's no relationship between those two sides, like a midpoint or anything else that would let me say this. So the only way to go about it is to demonstrate that these two triangles, TUV and WXV, are actually congruent to each other. And since these parts appear to be corresponding, then they would have to be congruent. Good. Well, the only thing missing here, we have two side pairs that are congruent, is we can use vertical angles to state that this angle right in here and this angle here. We can call them 1 and 2. These are vertical angles. And then that gives us enough to use side angle side triangle congruence. So from that information, we can say that triangle TUV is congruent to triangle WXV by SAS triangle congruence. Again, this isn't a full proof. I didn't write it all out in there. Not doing a full formal proof, but as soon as we say that, that allows us to say that we have these two congruent sides, that TU is congruent to WX by Cpctc. That's it. That's all we would have to do in a case like this. Well, not all. Technically, to do a full triangle congruence proof, to actually use SAS, there's a few statements that I'm missing here. I need to actually state that angle 1 and 2 are congruent, and I do actually need to state that UV and VX are congruent. But we can kind of see that, and we're talking about it. We're not doing a full proof here. We're kind of just showing how we're adding on this Cpctc element to something we already know how to do. All right, one more. I think one more after this. So when you're using Cpctc to do an actual full problem, there's kind of two processes here. First thing you always want to make sure you're doing is, let me clear some things off. I'm struggling with this. Okay, first, prove that we have congruent triangles. So if you don't prove you have congruent triangles, then you can't use Cpctc. So if you haven't done this, can't use this. Once we have congruent triangles, then hopefully we've already identified these parts we're trying to show that are equal are actually corresponding. And then there we go. We use Cpctc. It's pretty simple. Again, this is about 90% of the work, is showing the congruent triangles. We got to make sure we can write a good triangle congruence proof. Then add Cpctc on the end to show that the two parts that we're looking at are actually congruent to each other. So let's actually do the whole process this time. Thought this was pretty funny. You don't know how to do a problem. Cpctc. All right, here we go. one of the things that these Cpctc problems introduce that make it a little bit different than the triangle congruence proofs that we were doing before is we don't know what triangles necessarily we need to show that are congruent. We'd have to figure it out because there are a couple options here, right? We could be showing, for instance, this triangle here and then the one next to it right there. We could be trying to show those are congruent. That's an option. Alternatively, we could be showing that this triangle here is congruent to the other one, the one that sort of overlaps with it, MLK right there. And that's actually what we're doing this time. But let's talk about why we would do it that way. So we are given that JK and ML are congruent. And we are also given that angle JKL, which is here, JKL, whole thing, is congruent to angle MLK. So a couple things. One, just looking at the markings, this whole angle seems to indicate this bigger triangle versus that smaller one. But also the sides that we are trying to show that are congruent, let me just kind of do this in pink here. We're trying to show that JL, which is right here, this long length here, is equal to MK, which is this other one. And the only way that those are going to be equal is if we're dealing with those bigger triangles. So we're going to be trying to prove kind of right before the end here. We're going to be trying to show that triangle JKL is congruent to triangle MLK. Don't know how yet. One of our shortcuts. In fact, let's fill in a couple things that we know. We also know the givens will be in here, that JK is congruent to ML and angle JKL is congruent to angle MLK. These are both just givens. All right, we need to fill in this middle section. So far, as things go, we have a side pair and an angle pair. So we have an S and an A. So we either need to know something else about another side pair, another angle pair. And the only thing that seems obvious to me is this shared side that both of these larger triangles have. So that's what I'm going to go with. I'm going to say that KL is congruent to KL, or LK, I guess, would be the proper naming here, but that doesn't matter. It's the same side. It's a shared side. The other reason we give for this is the reflexive property. Something is always congruent to itself. Reflexive property of congruence. And that gives us a third piece to use for side angle side. We can look at our picture here. We have a congruent side pair, congruent side pair, and then the angles in between those are congruent. So these two triangles would be congruent by SAS. And therefore, the parts that we are trying to prove that are congruent would have to be congruent by Cpctc, since they are, in fact, corresponding parts. And we have shown that these two triangles are congruent to each other, so we can use Cpctc. Cpctc. I got an extra T on there. Got a little carried away. So, pretty short proof, and we just added one more step onto what we already knew how to do. We're going to do one more. All right, so here we go. We have YW bisects XZ. YW bisects XZ. So that means that these are equal. This statement is really leading us to say that XW is congruent to ZW. Definition of bisecting. So definition of bisect. That's what it means to bisect. So this is one of those situations where this statement is kind of telling me some markings that I make, but I do need to state that extra part in my proof. The other thing is XY is congruent to YZ. Okay. We also have a shared side. So we do have congruent triangles by SSS because of a shared side. So YW is congruent to YW, shared side. Pretty much have everything we need here, right? We are trying to prove that angle XYW, which is right here, is congruent to ZYW. Yeah, these are just corresponding parts. So we'll be using Cpctc with that after we show that the two triangles here are congruent to each other. So let's go ahead and write this proof out. It should be pretty easy. We start with the givens. YW bisects XZ, and XY is congruent to YZ. These are both given. Step 2, we could go a couple ways. We could state either one of these two things. It doesn't really matter which one. I'm going to go ahead and just put them in the order I wrote them down. So XW is congruent to ZW. And again, that was based on the definition of bisects here. So the definition of bisect. And then we had a shared side. So YW is congruent to itself. Shared side, reflexive property of congruence. Whichever reason you want to state on that, both of those are acceptable. That enables us to say that now these two triangles, this one here on the left side and this one here on the right side, are congruent by SSS. We have 1, 2, 3 side pairs that are congruent. We have to come up with some names for these. And again, it doesn't really matter what we name them as long as we're consistent. I'm going to go with XYW for my first triangle. X corresponds with Z, Y corresponds with Y, and W corresponds with W. So that was by SSS, triangle congruence. And then we wanted to state that these angles are congruent by Cpctc. So the angles were angle XYW. Remember, that's different than the whole triangle. Is congruent to angle ZYW. Again, different than the whole triangle because we're just talking about these angles up here. And Cpctc. Since we said the triangles are congruent, the angles have to be congruent because they're corresponding. Again, we're just kind of adding one more step. This is it. This is one more step to what we've already done. It's not that much harder, but turns out it's actually really, really powerful stuff. I'm going to briefly illustrate one example of kind of why we actually do this. Yeah, I'm going to do that right now. So let's say, so ignore this other stuff here, but let's say we're talking about a type of quadrilateral, which is called a parallelogram. So I'm going to draw a sketch of a parallelogram. So the definition of a parallelogram is that the opposite sides are parallel to each other. So when we say we have a parallelogram, it means we have a four-sided figure with two sets of parallel lines. Well, seems like there's more going on than that, right? It seems like there's probably more stuff going on. Kind of looks like these sides might be equal to these ones and then these ones. Kind of looks like maybe even these angles might be equal, or these ones. And turns out the way that we can prove this is by using Cpctc. So just for sake of discussion, let's say we wanted to try to show that the opposite sides were equal. Let's just focus on one set. Let's just say we wanted to show that AB and CD were equal. I'm not going to go about a whole proof here. but I'm going to illustrate it about what that would actually entail. Well, the way we could do this is be strategic. This four-sided shape, we could cut it into two triangles, right? And what we could do is we could try to show that these two triangles are congruent. If we can show these two triangles are congruent, then wouldn't these parts just be corresponding parts? Turns out, not too difficult. We have a shared side in between them, so we have kind of a freebie side. We have some alternate interior angles here, right? Alternate interior angles right there. And we also have some other alternate interior angles since we have another set of parallel lines. This angle here and this angle here are also alternate interior angles, which, well, turns out we got enough. We have ASA. These two triangles are congruent by angle side angle. So since those triangles are congruent, that means the corresponding parts are congruent, which means that these two sides are equal. Also means the other two sides are equal, or rather congruent, by Cpctc. So here's kind of a quick, not formal proof, but brief application of using Cpctc for us to prove some information about a quadrilateral. In this case, we proved that the opposite sides of a parallelogram are congruent. So this is our parallelogram, and we were able to use Cpctc again to prove that the opposite sides were parallel. I used prove loosely. We didn't write out a full formal proof, but we showed how it could be done. And that's the power of Cpctc, is using it to prove more complicated theorems by breaking shapes into triangles. All right, and we'll stop right there. See you guys later.